Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Tuesday, September 28th, 2021. I am delighted to be here with Professor John E. Bercaw. John, it's great to see you. Thank you so much for joining me today.
My pleasure, David.
John, to start, would you please tell me your title and institutional affiliation?
And my title is Centennial Professor Emeritus, and I'm in the Department of Chemistry. Well, I was at the Department of Chemistry as an active faculty member. I still have an appointment there as an emeritus faculty member at the California Institute of Technology.
Now, Centennial Professor, what is the meaning or the significance behind the word centennial? Centennial of what?
The professorship was offered to me as the first holder, and it was decided by the donors of the endowment to celebrate the 100th year of Caltech's existence. They chose at that point in their lives not to make their gift public, and they remained anonymous for many years, but then they finally caved in. They've given so much money to Caltech. I think they figured that it wouldn't change if their name was known to Caltech at this point. Of course, it was known to Caltech, but to the public more generally.
And who
They're,
who was that
they're
benefactor?
Shirley and Carl Larson.
I see.
They've also given chairs for the provost, whoever the provost is, supporting their activities at Caltech. I'll just put it that way. And I think they've given many other gifts to Caltech. They've been very generous.
John, what year did you go emeritus?
In 2015, more than 6 years ago.
And in what ways has going emeritus allowed you to shed administrative responsibilities and simply focus on the science that's more interesting to you?
It's not been complete, I'll put it that way. I'm still in some demand, although I've not been asked to serve on committees at all. I have voluntarily gone to Caltech for several years. In fact, I think for the first 3 or 4 years that I was emeritus status, I maintained a laboratory. I still have a laboratory, a noise laboratory. And my equipment is all there. And I went in the lab and did experiments myself. Something I've always wanted to do when I was younger was to do chemistry. Since I'm a synthetic chemist and I study reaction mechanisms and so forth, I still enjoyed it very much. And so when I was a full professor, especially, I had very little time to go in the lab other than when I was at group meeting and one of my group members was presenting something and I could see that student or postdoc wasn't doing the proper experiment or using the right technique. And I would actually go in the lab with that person and show them how to do it correctly. So I guess I've always been very good at experimental chemistry, and I never had anybody tell me that was very embarrassing for them. They were always very appreciative. And by the way, the group members always would crowd around the door to the lab I was in and watch with great interest to see what was going on. So I had a chance to go in there and work by myself, but I also helped out some of the graduate students in Taylor Gapier's lab. He's a professor in chemistry. He was one of my graduate students. And so he has a similar approach to chemistry, and his students welcomed the opportunity to use some of my equipment and to learn from me. And so I enjoyed that. I was still teaching in that way. Otherwise, Caltech has been very kind to me and not picked on me to do the things that I didn't want to do most of my career there. And that was serve on various committees and search committees for everything from the division chair to the provost. Um, so I was very active in committee assignments. I did not ever serve as division chair. I served as executive officer briefly, but I had other roles, like we had an academic officer position that was created by the division chair, and I served in that role for several years too. So I had a lot of committee assignments. We have standing committees in the division, and I chaired most of them at some point, including the one that takes the most time, and that's the so-called staffing committee. So I don't have to serve on any of those committees anymore, and I'm very grateful for that. And I spent most of my time away from Caltech after 3 or 4 years, especially when the pandemic struck, and it was advised by the upper management of the Institute that we should not go to lab unless we absolutely had to. So I minimized my presence there in the last almost 2 years now.
But you still have an active laboratory? You have graduate students and postdocs who keep things going?
No, I still have a little bit of research funding, but I don't have enough to fund a grad student, nor is it permitted as an emeritus status member. You can't have a graduate student. You can have a postdoctoral fellow, but since I have the second home in Arizona and I've been spending quite a bit of time there, I didn't feel right about having a postdoc that I would leave for as much as half of the time to work alone in the lab. But I do have a lab, and the last graduate student that worked with me, although officially signed up with my colleague, Teo Agape, she still voluntarily keeps my equipment going and fills the liquid nitrogen traps and when they're needed. And she checks on the glove box, the inert atmosphere glove box that I use. And she's one of the people I trained to know how that equipment works, and she's used it regularly. So she keeps saying, "You need to come back and use your laboratory. It still works fine, John. It's a beautiful lab." She always goes in and says, "Your laboratory is absolutely spectacular. I have never seen any glassware so clean and everything so tidy. It's a wonder. It's so different than my own group." And I guess I am sort of anal. So I don't spend very much time at Caltech now, but I probably will increase that time when everything is open, and it seems to be starting in that direction now.
John, a question we've all been dealing with, particularly for you being so far away from Caltech. How have you remained active in chemistry? What have you been reading? What have you been writing? What's been interesting to you in this past year and a half?
Oh, I still read some articles that people send to me just for my own information. They don't really request any feedback. But I don't regularly read the journals anymore. I have a full-time job here with my wife looking after our ranch. And especially this past year, because we've had a very severe monsoon season, and we've had several flash floods run through our property through a wash that wiped out some fencing that helps keep our dogs contained. So I've been working the last 3 or 4 months just getting those fences repaired. But I've enjoyed myself doing something different. I am an amateur photographer, and this part of the world is really beautiful. So I've been out taking pictures and things like that. But I haven't been up to speed on my chemistry. But I do look at the Caltech website and all of the emails I get from various people at Caltech, and I try to respond when they ask me for letters of recommendation, and the former students and current students and postdocs, and I have a bunch of them. There are over 150 of them, and many of them are in academics themselves, and that requires regular nominations and for promotions and various other jobs. So Mostly it's been an informal, not an intense, focused reading of the literature. Um, but I'm very happy. So I guess I'm doing the right thing.
That works. John, before we go back and develop your personal family narrative, I'd like to ask a few very broadly conceived overall questions about your research and your approach to chemistry. So first, perhaps at the most fundamental level, your field of synthetic chemistry, do you see chemistry essentially broken down into two parts, organic chemistry and synthetic chemistry? Is that the proper binary from which all chemistry goes?
No, I wouldn't say that's the way it breaks down. People who make molecules are called synthetic chemists, and people who study the reactions and the mechanisms of those reactions and try to apply the benefits of those new molecules. Those are from all fields of chemistry, not only organic chemistry, but most organic synthesis is conducted by organic chemists. But physical chemists study these things using modern spectroscopic techniques and increasingly computational methods to sort of rationalize why we see what we see and make even predictions, although those predictions are still coming on. They're very difficult to make, of course. The traditional ways in which chemistry is broken down is by area of chemistry. So physical chemistry or chemical physics, some people like to be called physical chemists, others prefer chemical physics. They use spectroscopy and the methods I just said. Organic chemistry is consisting of both synthetic and mechanistic people, and many people do both synthesis and mechanism. And then there's inorganic chemistry, which is really the closest thing that I am. And I grew up as an inorganic chemist, and that means not so much having to do with traditional definition of organic. It is not organic chemistry, and so inorganic chemistry is the chemistry of all of the elements, including carbon and nitrogen and phosphorus and sulfur and things that organic chemists study a lot. So we're broader. We look at elements in the entire periodic table. And it's a relatively new area. And in fact, I think we're now celebrating maybe even our 50th year of being a division of the inorganic of the American Chemical Society, the inorganic division. And Harry Gray was one of the people. I don't know if you've heard of Harry Gray, but he is a very distinguished chemist and a great joy to be around, and one of my very, very best friends. He hired me along with another person at Caltech. And so we remained close. In fact, we email each other regularly. Anyway, Harry was part of the reason why the Division of Inorganic Chemistry was founded. So that's another area. And as I said, it focuses more broadly on all of the elements and involves synthesis, and especially early on, structural determinations using X-ray diffraction to get the so-called crystal structure of these molecules that we're making, and also to study the electronic structure of these materials that inorganic chemists study, because they have metal centers that have these D and F orbitals that aren't usually involved in bonding for organic molecules. And these are of great interest and give them the beautiful colors that they have. And the applications are often involving photolysis of the molecules and looking at what the excited states do and what the emission spectra look like and so forth. Because inorganic molecules are making up biology as well. And that brings me to the next big area of chemistry, and that's biochemistry, or again, chemical biology, depending on who you are and what you prefer to be called. And so there are those four areas that are in most departments considered to be the breakdown of the various parts of the chemistry department. Especially in the Midwest, but also in a few other schools, there wasn't an area of chemistry called analytical chemistry, which is what it sounds like. It is the study of methods that are used to study, to analyze the molecules in terms of their constituents, but also to do things like electrochemistry, where we study the oxidation and reduction properties of them and what you can learn from that. And that's not so popular anymore as a separate part of chemistry, except in a few schools traditionally have been very strong in analytical chemistry. In fact, Caltech had a couple of analytical chemists, and they're gone. They retired, and that was the end of the analytical division of Caltech. And that's probably our loss. But now, more recently, there's a materials chemistry also that's growing up and will probably be its own division, is my prediction, eventually. That will be its own division of a chemistry department is material chemists. But chemistry is at the interface of a lot of other disciplines like physics and biology, and as I just said, material science. That's because, well, some of us think it's the central science, and so it's only natural that we will be tied into other fields through chemistry, because chemistry is materials. But back to your question about synthetic chemistry, I think that people who make molecules are unique among the sciences. We have that gift. We can make pretty much anything we want these days because synthetic chemistry is so well developed as a pursuit, and we know how to make things in so many different ways now. So we have that unique thing among all the sciences, is that we can create new matter. I guess you could argue that nuclear physics can do that too, but we're talking about molecular things now.
John, do you have a sense of when the term synthetic chemistry first came into wide use?
Wow, I don't. It's been a long time ago, maybe 200 years ago. I'm just making a guess, but it grew up in Germany. Chemistry grew up in Germany, but it wasn't only synthesis, but a lot of the early parts of chemistry were in making new molecules and seeing how elements combine with one another. And then more recently, I guess in the last century, synthetic chemistry has been a little different than what it had been traditionally, in that we can have so-called synthetic targets. We want to make a molecule that has this structure, either because it might be a model for some biological active site, for example, like in hemoglobin, where the heme iron center is where the action is. So people made these molecules on purpose. And it's gotten very sophisticated, especially in so-called natural product synthesis. And these are very complicated looking structures that are very precise in their structure, not only in the connectivity, but the stereochemistry. The sum of the parts of the molecule can be are commonly optically active. That is, their mirror image is not the same as it. So it distinguishes structure in that way. And making stereochemically pure molecules is really challenging. In fact, I call these complex molecular targets that these people sometimes spend the part of their career on, like vitamin B12 was a success story, and many research groups targeted that. It has a cobalt center, in it, and it has a lot of complex molecular structure around it, and its function in nature is remarkable. It's mainly at the Cobalt Center, but getting all the stereochemistry right, the connectivity right, took many research groups, years and years, competing with one another to be the first one there, but also working together to make the true structure.
John, as I'm sure you've heard, physicists like to use the metaphor of a pyramid whereby physics is the foundational science, and then up from that is chemistry, and then up from that is biology. But from how you're talking about chemistry being in the center, perhaps that's a metaphor that does not make the most sense for you.
You mean the pyramid metaphor?
That's right.
Yeah. No, it doesn't make much sense to me. I think of it in terms of, I think I grew up being distinguished in the following way. Math is the purest science. Everything is, well, I guess it's in modern math, it's not necessarily that clean, but, there's just one solution to a problem, and it's precise. And you can apply all kinds of logical progressions to get to the answer. Physics is a little, based a lot on math, but it also has a few things that aren't fully understood in the very depth of the field. They still are asking questions about states of matter, and especially in very high energy situations. They don't know what really goes on in some of the plasmas and so forth, and they're still modeling things like that. So it's not quite as pure as mathematics. Then chemistry comes next, and we have more and more things that we don't fully understand. But chemists have been very clever. They can build intuitions by doing chemistry, and then that guides them in understanding new things. But we can't solve the electronic structure of a complicated molecule with the precision that we would like, because the Schrödinger equation is just simply not solvable for things as complicated as molecular problems. In fact, when I was teaching freshman chemistry at Caltech, I had 220 students in Chem 1A, and I introduced them to the field by saying, it's a complicated field. We can't solve everything in closed form like you're used to doing in physics and math. And you have to somehow become comfortable with just guessing what the correct thing is, and just accept that it happens, and these are the products of the chemical reaction. And we can't solve in closed form why if you pour water on anhydrous aluminum chloride, you get hydrogen chloride and aluminum as products. It's just not solvable. But we know that, and we build on that observation to predict other things. And then I always end that discussion by saying, there was a famous quote, and I've now heard that it may not be actually accurate, but I heard a quote that said, Albert Einstein said, the problem with chemistry is it's too complicated for chemists. And I think that says a lot.
John, for you then, with chemistry as the central discipline in your overall research agenda, when do you find the research taking you more into the physics realm, and where do you find it taking it into the biological realm?
Maybe you should say that question again, because I'm not quite sure what you're asking me.
In your research, when are principles of physics most important? And where in your research are biological considerations most important?
Well, I don't think we can predict those things, but I can tell you that we don't generally choose to work, for example, at the interface with biology unless we have some interest in the biochemistry of what we're doing. And maybe something else is of more interest to us, for example. And the same could be said about physics. We don't work with molecules and at the energy level where the electrons are dissociating from the atoms and the molecules are falling apart. We don't work at that realm, but we still have applications. For example, it's hard to say what shining light on an inorganic solid is, chemistry or physics, because we're hoping we can see some electronic response to that solid material, for example, as a semiconductor or photocell or some application like that, or apply a field across that solid and have a semiconductor. But but some people choose to study the chemistry side of those problems, but they have more physics application. And by the same token, some of the molecules that we make, we don't anticipate that they're going to have spectacular physical properties that physicists would be fascinated by. For example, especially with the so-called F block and D block metals, their molecules sometimes have very high magnetic moments and are of great interest because they have so many unpaired spins in them. And so we make these molecules. Sometimes we're building on something that's similar to what we're targeting, but sometimes you just come across by serendipity that this thing has an amazing magnetic moment, and there are as many as 7 unpaired spins on them, or even more. When you start adding the unpaired spins on the ligand systems, the groups that are bonded around the metal atom. And so at that point, we bring in physicists, or they get interested hearing a lecture by one of us, and they approach us and say, we would really like to have some of that material and study it. And so that in that way, we interact with each other, the physicist and the biochemist, with the chemist. And the chemists choose or not choose because of their own interest and their own expertise to study something like that. In my own work, I think the one area we haven't discussed, and that is catalysis. And I don't know if you remember your definition of a catalyst, but from chemistry, it's something that makes a chemical reaction proceed more rapidly without undergoing net change in itself. And those are the kinds of molecules that I've targeted in much of my work, especially in my later career, where we were trying to make a catalyst that would perform something of interest to industrial chemists, for example, or even people in industry trying to make money from these chemical reactions. And so their chemists get involved, but also chemical engineers get involved traditionally, and physicists, and not so much biochemists, but many of the molecules of interest to inorganic chemists are involved in enzymatic transformations, which are catalytic reactions that occur in life. And so catalysis is a sort of all-encompassing interest to many fields, and including my own. And so when I discover a catalyst, industrial people will come to me and say, hey, that's really interesting. Could we collaborate with you and see if we could understand it more and maybe make some changes in it that might make it more practical or work better? I'm welcoming of those kinds of interactions. And I learn from people who have experienced much of catalysis was discovered by accident and developed by trial and error. And now we have a more molecular understanding of some areas of catalysis, and so we can change for the better, hopefully, the catalytic process, and make the the product cheaper and more plentiful, and maybe even greener. Greener is a lot in the foreground for chemists these days. We're trying to dispel this negative impression we have of polluting the world.
John, on the question of working with industry, is your research set up in a way where you're always after basic science questions and then you think about applications, or sometimes your starting point is thinking about applications? I wonder if you can talk about the sequencing of the relationship between basic and applied science.
Yeah. Well, there are some chemists, and I guess I'm somewhat in that group, who just have money from federal government mostly, but sometimes even from industry, to just make something interesting and new. And new is really the most important word there. And so they're given sort of free license to pursue anything they want. But increasingly over my career, I've noticed that people who give money to chemists and to scientists in general would like us to have some, in the back of our mind, some sort of application in mind. And increasingly, it's been, topics that are world important problems like climate change and related to that, energy and making things that aren't so polluting and so forth. So I often have to justify in my research proposals that I send in to get funding so I can do my science. Start out by saying these are the big problems we're trying to address in my group, and maybe it has application in several areas. And then I sort of work my way down to saying why we're doing the experiments we are. A lot of times we think that, and I'll go ahead at the very beginning and say that this is not necessarily true, but we like to think that by studying in great depth how things work and what the structures of molecules are, we can improve things and we can make new things. Even perhaps beat nature at doing something that we would like to do, like fixing nitrogen to ammonia, or making dioxygen from water and sunlight, like photosynthesis does. So we think that if we understand these things in enough depth, we can create something that's more efficient and therefore better and less polluting or whatever, cheaper. And so, I almost never have the freedom to go and work on something that I find fascinating with no application in mind. There was a time when agencies like the National Science Foundation would say, okay, you can have, they would even give you a percentage. Maybe one day a week you can work on something you just find fascinating, but you should spend most of this money and your time on the project that you're describing that you've justified as having some ultimate application. In a way, it's sort of frustrating for us because we don't forget that we're educators and we're trying to excite students to go into chemistry and do their own thing and be creative and so forth. And often that's true if we're working on something we really love and want to pursue, no matter what the ultimate application. But increasingly, students, I think, can get excited by problems and maybe even more excited by problems that have an important application. That this process that I'm looking at is part of a bigger problem that I'm trying to impact. And I admire people for having that ultimate goal in mind when they're studying chemistry. But as an educator, I like to excite my students. I often say when they're coming to me to ask about joining my group, and they say, how often do you make people come to the lab? And I say, I don't have any time like that. I want you to be excited by what you're doing, and I want you have to drag yourself out of the lab late in the evening, and I want you to get up early in the morning and charge in there because you're so excited about what you're going to do that day. Of course, that's a romantic ideal, but that has worked very well for me. Exciting students and getting excited myself by it is a great motivator. And I think when we're planning our approach and so forth, excitement is a very important driver for my field. I don't like doing mundane things. I want to do something exciting and something that I really, truly enjoy.
John, this is as much a cultural question as a scientific one, but over the course of your career, have you noticed increased appetite or willingness in academic scientists to be involved in industrial applications where perhaps early in your career there was a more ivory tower approach where we only do pure science and we don't get involved in business, and today perhaps that's really not the case at all? Have you detected that transition over your career?
Oh, yeah. When I first started, gosh, I don't know, almost 50 years ago, many people wanted to just work on fundamental questions. And for example, in organic chemistry, physical organic, as it was called, that's the study of mechanisms and all the intricacies of how bonds are broken and made in reactions. Physical organic chemists like to do very so-called fundamental research where we learn the rules and the laws, if there are laws of how things are supposed to go together and how things won't go together in some other way. They like very much to be in the ivory tower because there was no immediate applications to understanding why 2 + 2 was firmly forbidden and maybe photochemically allowed, that kind of thing. It doesn't have immediate application in industry. But over time, it got harder and harder to get funded to do that kind of work. And so people began to work more and more with industry. And industry, more than the main funders of science and academic labs, chemistry labs like the National Science Foundation, the Department of Energy, and National Institutes of Health, they wanted to have some sort of application, and often industry drove those preferred areas for funding even in the federal agencies. And so, if you could make just any old molecule in organic chemistry, why not make a pharmaceutical or make something that can be used in health? Or so more and more we sort of sold our souls for the research funding that we needed to do our science. And it wasn't all bad that we were doing that because people didn't like this ivory tower approach. And it was much more arbitrary who gets the money if you're doing, ivory tower things. Chemists like to give good scores to proposals that are doing science much like they're doing, or more, they're more interested in than something that's going to have an application. And as time went on, I think we got more and more involved with industry. And as you probably know, in my last part of my funded career, I worked with what was called British Petroleum, with BP. And BP bought various other chemical companies, petroleum companies, petrochemical companies, and got bigger and bigger. And then now they just say BP means BP. Doesn't mean British Petroleum anymore. It's bigger than British. But anyway, BP came to us. They actually sought us out in my research group and asked us if we would like to prepare a proposal for a very large grant that would be part of a great collaboration with BP. And we would just do fundamental work, but we would listen to BP about what was most interesting to them about what we were doing and so forth. And it sounded too good to be true. Well, we prepared a proposal at Caltech. I was leading the work they were interested in, along with my colleague and my very good friend and collaborator, Jay Lebinger, who is still at Caltech. He is the administrator of the Beckman Institute, and he started out working with Harry Gray in that role, and he has continued as administrator as the director of the Beckman Institute has continued. But he is an organometallic chemist like I am, and we started collaborating right after he came to Caltech. He wanted to work with graduate students. He wasn't able to direct on his own these people, but he worked with my group mainly, but a few other groups as well. And he is an incredible intellect and a very creative guy. And we were working in this area of carbon-hydrogen bond activation, which has important applications in making liquid fuels from gases like natural gas. Methane is a major component of that. And so we had already worked in that area and published a few papers that caught their eye. And so they wanted us to bring in some other faculty, and so Bob Groves and Harry Gray, and Mark Davis, and a couple of others, including Jonas Peters when he was first at Caltech, and then later Teo Agapier. We were the Caltech team, and we presented our proposal to this group of reviewers that were going around the country to, I guess, about 10 or 15 schools that sent in proposals in response to their invitation. And in the end, Caltech won this competition, but so did Cal Berkeley in the chemical engineering department. So the chemists were going to be at Caltech, and the chemical engineers were going to be at Berkeley, and they split the amount of money, which was still a significant amount, and supported a large number of graduate students and postdocs and a few undergraduates for an amazing, by the time it ended, it was down to just Jay and I. In the end, we were the only ones in for the last 2 years, but it went 17 full years, which was unheard of in corporate research of academic science. And although they kept sort of, some of the people who were coming to our joint meetings kept saying, well, how is this going to help make money for BP? And we would just ignore those questions because the management of the program kept saying, you should apply your own ideas and develop your own reactions. Don't just listen to us. We want something new. The problem they were asking us to solve initially was to convert methane into liquid fuels like methanol or gasoline. That is an amazingly tough problem. And of course, industry has been wanting to do that for decades, and they haven't figured out how to do it. But there were some hints in the literature, though, we were getting close to having something that might even be practical. And this is my own interpretation. I think that the BP management said, okay, these are smart guys at Caltech. They're not going to solve this problem. But if they do solve the problem, it would have such a disruptive effect on all of the petrochemical industry that we need to know about it early on. And even if they don't solve it, they're going to be able to keep their ear to the ground and know who might be close and keep us appraised of, go read these papers. And I think these are right, to be judge and jury for them all too. But so they were pleased with it in the end. They kept saying how pleased they were because they knew we were trying to solve this problem, but we had our own approach, and it was lots of fundamental science, and they believed that if we understood the fundamentals, we would be able to have a good chance of solving the problem. They never hired very many of our people, but they loved working with us, and especially as a scientist in industry. A lot of them are envious of academics because they like to teach and they like to educate people, and they think we have the perfect job. Well, we do, but they wanted part of it. And they enjoyed talking to our students and postdocs as well as us. So there is a case where industry really invited us to submit a proposal, and they funded us for at least 10 years longer than they had funded any other project in the history of BP funding academics. So we've gotten that far, but there's another extreme that has another direction that's also rather extreme, and that is that people work, especially in the biochemical area, the medicinal chemistry areas, and they make a discovery that has real value to health or some other areas, for example, in energy-related things and so forth too, but especially in the biological chemistry area, that they make some sort of breakthrough that looks like it might have commercial value and it's not being produced yet, they'll make a startup company, and they will be involved in lots of activities with those startup companies, and that'll take away from their academic research, but maybe also in a positive way, it keeps them working. So in that way, they're actually helping form a company. And for a while, it seemed like my colleagues that were most successful had at least one startup company too. And some of us, Harry Gray and I, most determinedly said, no startup companies for me. So we didn't ever pursue that. But many of my colleagues at Caltech and many people around the world were involved in various startup companies. And so in that way, I think they get really close to working in industrial and related things.
John, I'd like to ask you about
all of this is developed. Go ahead.
I'd like to ask you about the theory, the role of theory in your research. In other words, when you're thinking about setting up an experiment or how you have your laboratory set up, in what way does theory orient the kinds of questions you're asking at the outset and to know if you're on the right track with what the results tell you?
When you say theory, do you mean computation, or do you mean that my colleagues in theory don't think they don't have great respect for people who do computations. They just, turn the crank that somebody else has developed to compute something. Theorists are people like my colleague Rudy Marcus, who actually conceives of how things work and then develops a set of principles by which they can make predictions and so forth. I don't do very much of that. People like Harry Gray have done much more of it. Speaking of Rudy Marcus, Rudy predicted that the rate of electron transfer would increase with driving force until the driving force got to a maximum point, and then if the driving force got too large, it would then slow the reaction down. And so that was the so-called inverted region when we went over the maximum of that curve. And people like Harry developed, and other people in Chicago, Gerhard Kloss and so forth, they actually built molecules to change the driving force over that curve and to look for the inverted region. And so that was the driving force for them. And actually, they both found it. And Rudy was delighted, of course, because he made this prediction based on his very fundamental ideas about electron transfer rates, which he got the Nobel Prize for, by the way. So I don't think I've ever done that, where I've actually designed molecules with that kind of application. That would be mainly in physics or physical chemistry.
I was thinking more along the lines of, when you set up an experiment, how do you pose the questions that inform the experiment, and then how do you make meaning of the results if there isn't some presupposition about what you might expect the experiment to tell you? I was thinking theory more in a more nuts and bolts sense.
Okay, so you were thinking of, this is our current understanding of how this reaction is happening, so we need to design some experiments to test the validity of that assumption.
Right.
Yeah, that is very common. Everybody does that, including I. So, well, it's a very very complicated question because there's so many different things we're testing for, but we often have an idea um, about how something that we just observed took place. And so what is the mechanism? What is the stoichiometry of the reaction? That is, how many molecules of this make how many molecules of that? Um, and then we sort of at a group meeting discuss how are we going to test this? What would be, if it's option A, what would be the prediction of this experiment that we think up? Like how many molecules of oxygen is involved in the reaction? And then we have to decide, well, how are we going to determine how many molecules are going to be generated? And that's sometimes not trivial. I mean, you can't count molecules one by one, at least not very easily. And so, whoop, I hit my keyboard, okay, I hit my pad. Anyway, so for example, we would go to the laboratory, and on a vacuum line in my group, we have the capability of determining how many moles of oxygen is involved in this reaction. And so we would weigh out the reagents so we know how many moles of reagents we had. And the oxygen that's involved would be transferred around the vacuum line into a calibrated volume and its pressure and temperature measured. And then we'll know how many molecules of oxygen are there. So we have this special piece of equipment that was designed for answering just those kind of questions. Excuse me. And so we would think that up in group meeting, and then we would decide how we're going to do the experiment, and what we have to know how we're going to, we know it's oxygen and so forth that we made. Sometimes we'll use different isotopes to answer questions that, option A goes by this mechanism, then we would predict that the isotopes would scramble completely or would be forced to just make one isotopolog, that is, has one isotope of this atom and an isotope of another atom. And we can make those measurements as well. But those are the kinds of questions that we ask. We also ask questions that will have a spectroscopic answer, where we would predict its NMR chemical shift. Some nucleus in the molecule would appear in the NMR spectrum in a certain region, and we will go and make that molecule. Sometimes we have to enrich it in a thing like carbon-13 or nitrogen-15, which is very low natural abundance, so that we'll get a good signal. And then we'll look in the NMR spectrum to see if our option A or option B is the correct one. Sometimes it's a totally unexpected result. And I did that very early in my career, where the amount of N15 that came out in the hydrazine that we made was not as expected. And it forced us to a different conclusion than we had made earlier, that we were wrong about both of the options we had. And it was actually a third option that we hadn't thought of. So those are the kinds of experiments that lead you along and get you into something unexpected and often very important that you missed.
John, some broad questions on the role of technology. So first on the side of instrumentation. Over the course of your career, what have been some major advances in instrumentation that have proved to be a game changer, not only for the types of experiments that you do, but the answers that these instruments yielded?
Wow. Well, it's still going full speed, and I don't even understand all these new methods that are coming out. But certainly I think, like in organic chemistry, NMR spectroscopy was a game changer. When I look back at how organic chemists used to have to great lengths they would have to go to answer the question about the structure of a molecule, it was incredibly slow and painstaking compared to making the molecule and putting it in an NMR spectrometer and looking at its spectrum. And now we understand it in 10 minutes. what the structure is. X-ray crystallography is also very important because that gives you a very detailed picture of the molecule when you solve the structure. And that's become easier and easier. Now, anybody can use the computers to solve it. There's some pitfalls you have to be careful about if you're not a pro, but graduate students regularly solve their own X-ray structures, where it used to just be a PhD thesis to solve the structure of a molecule. Now it's something you do in as little as a couple of days. You have this three-dimensional structure because the spectrometers are now so powerful, and the methodologies for solving the diffraction patterns and translating that into a three-dimensional structure are so very powerful. And now we have coming along more recently where you didn't have to grow a perfect crystal of the molecule in order to get a crystal structure. You could get a microcrystal and you could solve it with electron diffraction. And you could solve particles, little crystals, microcrystals as they're called, that you can see with an electron diffraction, electron microscope, and then you can do diffraction on the molecules, the crystals, microcrystals individually, and solve several structures from a complex mixture of things, which is unheard of. And it's very expensive, the instrumentation. It's not as easy as I made it sound, but it is coming along, and it's something that would change the way people who make molecules get structures. You don't have to have an NMR spectrum that you have to interpret. You don't have to grow a crystal that's big enough that you can put it on a fractometer and solve the structure. So those kinds of things have made a big change. And I have to say, although I'm perhaps one of the biggest critics of computation, I think that theory and computation have come along and are changing the way we think about the bonding in the molecules and the spectroscopy of the molecules and the reactivity of the molecules. And these people are able to predict it. They oversell it, and I can see why they do it, but it does guide the way we think. And many people who do computation, I have a colleague named Bill Goddard, who is a theory computational type, and he loves to talk to experimentalists because he wants to know what are the questions you really want to answer with these techniques, and then he focuses his research on that. He sort of is driven by the experimental findings, and he makes predictions, and sometimes he's actually right about things that I find amazing. Sometimes he's wrong, but he's an easy-go-lucky guy, and he's happy in either way.
Now, when you say, John, that you're a critic, you've been frequently a critic of the computational approach. Where are you coming from? What's the framework by which you're making these critiques?
Okay. Well, there are various theories, and one of the ones that was very popular, it still is very popular with people like me, organometallic chemists, is something called density functional theory. And it's not sort of intuitive to somebody who thinks about molecular orbitals and atomic orbitals, mixing to make molecular orbitals. It minimizes energy using so-called density functionals. And I'm not a big, I don't understand in great depth how density functional theory works, but it has been amazingly good at predicting the electronic structure of molecules that people like me make. And in other cases, they take it a little bit too far and ask questions that are a little more difficult to answer. And they will apply the theory, but they have a variable that they often don't tell you about. And that is, there are different density functionals that you can use to do the computation. And these are tabulated. Places like Los Alamos have a very popular set of density functionals. And if you use different set, you get a different answer than if you use another set. so people are sort of casual about saying, well, I used this one and I tested these other ones. And so I get a little bit impatient with people like that don't do the controls. But have you, for example, when I was consulting with Exxon, they were very interested in my reaction to their density, in my reaction to their new theory department. And so they had them come in and talk to me. And I said, have you applied your density functionals and your density functional theory to answering these questions that we don't, that we already know the answer to, we already have the result, and does your theory predict that result? Or that they're always trying to solve, the unknown problem that we haven't encountered yet. When we would love to solve, they do a calculation on how you might do that, and this theory says you can make it this way, for example. And I said, well, why do you have confidence in that if you haven't done the basic thing, like the control experiment, where you calculate something you already know the answer for, and then you get that answer that we already know is right. Then you have some confidence that maybe for this other problem it will work just fine, and we have enough confidence to actually go out and try it. And some people do, in fairness, do those controls, but early on, it was. I have a colleague named Jay Winkler, who's also a member of the Beckman Institute, like Jay Lebenger is, and he has an even lower opinion, I think, than I do of some of this computation. And he said, "Well, yeah, density functional theory is sort of like Wikipedia. You can do density functional theory. It's sort of like looking up a question in Wikipedia, and you'll get an answer. The problem is you don't know whether the answer is right or wrong, and that's true of Wikipedia, and that's true of density functional theory. Although Wikipedia is pretty good, they have pretty good controls on making sure there's no bogus websites there. Anyway, that's the basis for my reluctance to put a lot of faith into the calculations.
John, what about the value of computation both for data analysis and simulation for your research?
Well, computation is very important for analysis. For example, electrocrystallography. There are also software packages that will predict the NMR spectrum of a molecule you can draw on a computer and transfer it into this program, and it will predict the spectrum for you, or for many nuclei for that matter. And so you can get some confidence that you made the right thing if you get that one that's predicted by the theory. And it can go on and on with the various methods that are used for structure determination. That the theory really is important in that way. But it doesn't. It sometimes does stimulate me to do experiments to test the validity of them, and people do that regularly. And often they find it is right, and often they find it is wrong in its prediction. So I don't use theory to guide me very often, but sometimes I do. For example, there are some rare phenomena, not so rare, but not very common phenomena in chemistry where you have quantum effects coming into play, especially when hydrogen atoms are moving around. And you can have tunneling phenomena that give very large isotope effects. So if you change from hydrogen to deuterium, you get, rather than the classical prediction of a limit of about 7 to 9 at room temperature, the deuterium goes slower by a kinetic isotope effect of about that. You get something like 100 or even higher values. And those kinds of numbers can't be explained by classical theory, and you have to go to computation, and you can predict it, I guess, from that, where there is actually a quantum mechanical tunneling through the barrier that happens, and that's why deuterium is so much slower than hydrogen, because hydrogen tunnels much more effectively than deuterium, just based on mass. So there are things that we've done. We thought we had a way in which we could look for this anomalously large isotope effect and predict something about the mechanism. And so Jay Lebinger and I had a graduate student who made many isotopologues, many different structures to test the generality of this prediction. And we were doing great for a while. And then we started getting exceptions to our prediction. And we had to publish a paper saying, no, we weren't right about that. What we said earlier is wrong. And there is no correlation with mechanism here. So sometimes it does stimulate us to do certain experiments, but it's not that common.
John, we can now get a little more specific in terms of nomenclature. So let's start first with metal chemistry. So there's structural organotransition metal chemistry and mechanistic organotransition metal chemistry. So let's start at the most basic. Would that be metal chemistry and then organotransition modifies metal chemistry, or how do these words work together?
Well, when you say metal chemistry, that's not very accurate. Nobody works with the metal, the element. We work with structure, with molecules that have that metal in it. Well, we tend to call those coordination compounds. Those are classic compounds. For example, you put 6 ammonias around a cobalt ion, that's a coordination compound. That's not an organometallic compound. And that was developed early on. Alfred Werner won the Nobel Prize for his contributions to that area of transition metal chemistry. And people will, when I teach my course, I start with classic coordination compounds where we have things like ammonia and chlorine ions and water coordinated to the metal ion. It's almost always the metal in some higher than zero valent oxidation state. And we predict something about its color and all of these kinds of concepts that come out of understanding the bonding in these coordination compounds. And those are then translated on when we start to put what are called stronger field ligands, like carbon. That's when you have a metal carbon bond, then you have an organometallic compound. Sometimes it's something neutral like carbon monoxide. You can put 6 carbon monoxides around chromium atom, and you get a beautiful white crystalline material that sublimes, even at room temperature some. And yet its electronic structure is very different than if you had ammonias around the chromium. In fact, you can't even get the ammonias to stick to the chromium if it's in the zero oxidation state. It has to be higher to pull these lone pairs on ammonia into the ion. Carbon monoxide molecule has very different bonding from ammonia. So these kinds of things are different in that classical compounds, the ones that were made first, that have these donor groups like oxygen and nitrogen and chlorine and other molecules having lone pairs on the binding atom. Those molecules have guided our thinking about how we changed it when we made all of these so-called stronger field ligands, those that have very strong carbon donors. Carbon anions are incredibly strong donors because carbon is not very electronegative, and it wants to push its electrons to whatever it's binding to. So methide CH3 minus is an incredibly strong field ligand. But things like carbon monoxide are also, even though carbon is not a very strong base, it's hard to protonate the carbon in carbon monoxide, but it has molecular orbitals on the molecule, CO, that interact really well with the d orbitals on the metal and makes very strong bonds. And all of these things came from making these metal carbon containing molecules and looking at their electronic spectra and other features that made us question how different they are from the classical coordination compounds. So organometallic chemistry started out very simple things like diethyl zinc was made over 100 years ago. And it's a very dull molecule. I mean, it's very useful for making other things, but then the big breakthrough is when we as chemists made ferrocene, which is a so-called sandwich compound, where an iron, formerly in the +2 oxidation state, sits between two 5-membered rings that have 5 carbons and 5 hydrogens. And so the iron is sandwiched in between those two ligands. And that class of compounds really started out. I'm going to have to go get some water.
Sure, take your time.
Can you stop the recorder? Yeah. Hello, Mark. Okay, I'm back. I'm not used to talking this much.
Yeah, you need to stay hydrated.
Unlike when I was working. So I mentioned ferrocene and its sandwich structure, and then that was really the birth of modern organometallic chemistry. And that the field is really new, but it really began with that discovery. And then all kinds of different carbon donating groups, not just C5H5, but more elaborate things were made, and everyone was fascinated with what was possible. And then some of these turned out to have really interesting redox properties. They carried out transformations on other molecules in catalytic ways. And they gave people new ways of making organic molecules. So they were used as catalysts to make molecules or stoichiometric reagents. And they were found out to be really important molecules in making new molecules no matter what field they were in. And also in industry, they started to be used to make commodity chemicals like methanol and acetic acid, polyolefins. That's something I've been very interested in. And so I've been fascinated by metallocenes much of my career. I started out working on that, even when I was in graduate school. And these things were really interesting. I think most people would find them interesting, even if they weren't working with them. They're still fascinating. So it is true that we tend to start out with something that's simpler, make something more elaborate, and find out it's more complicated. Many of the properties are those that you would predict by changing in the way you change the molecule, but you have to make a few of them to see what are the principles here. That is, what would you predict if you made this change would happen? Okay.
John, what about the role of stereochemistry? How does that fit into your research?
Okay. Well, I think the main place that it's fit in, although we've used stereochemistry to answer questions in the past, but a place where you really want stereochemistry to be exact is in the structure, oh God, in the structure of a polyolefin called propylene, polypropylene. And that's been one of the most fascinating things in the polyolefin business. I don't know if you know what that encompasses, but things like polyethylene, there are more than one type of polyethylene. Polypropylene, then there are polystyrenes and all kinds of polymers that have heteroatoms on carbon and hydrogen. Things like oxygen and nitrogen in the polymer structure. But many of these polymers, other than polyethylene, have stereochemistry in the structure. So I'm going to cough my brains out here. Okay, let me finish this and then I'm going to quit. Propylene is what we call a prochiral molecule. So depending on, so I'm holding up my finger and the metal atom is approaching to coordinate the propylene and make the polypropylene, which is hooking the polypropylene units together. Depending on which side of the propylene it approaches from, you get a different absolute configuration at the carbon of propylene that has a methyl group and a hydrogen on it. Remember, propylene has a double bond between a methylene group and a CH3 group. So if it comes in every time from the same face, the metal atom that's approaching the new propylene molecule that's going to be added to the chain, it will make something called isotactic polypropylene. And that molecule has high crystallinity. It has a high molecular weight. It coils, individual molecules coil and pack very well in the lamina and so forth. And all of that leads to mechanical properties that are highly desirable. If it had no preference for which face of propylene it coordinated to, it would make something that's stereo random, as we say, that's so-called atactic. And it's just a gooey mess. You can use it to patch holes in your roof, and that's about the best thing you can do with it. So nobody wants to make that kind of polypropylene. Well, maybe not nobody, but most people don't. There's an enormous market for isotactic polypropylene because it has resilience. It has lots of uses where it is tough and it melts at a high temperature, way above the weight of water. And yet you can melt it, and it's called a thermoplastic. You can shoot it into a mold or extrude it and as a liquid at high temperature, and then when it cools, it becomes tough and hard. Although polypropylene isn't particularly hard, it is much tougher than, of course, a liquid. And some polymers that you make are not thermoplastics. If you don't heat them hot enough to melt them, they actually decompose. So thermoplastics are highly desirable. So my group had to try to understand why certain kinds of molecules that were catalysts for making polypropylene from propylene monomer did so in a stereo-regular or stereo-preferred way to make isotactic. And some were making this worthless form. And so that was a place where we had to design a molecule that was, to answer the question, that was so-called stereo pure. It had a chiral center in it that directed the ligands around the active site. It was a zirconium that was often used as the catalyst for this. And so we were able to show that it's not just the propylene approaching the chiral metal site. There's some substituents that made the methyl group interact with one if it was up and not interact with that one in a more favored way down. And that direct interaction of the groups around zirconium with the incoming propylene was thought to be the important feature. But we and a few Italian people also knew this from the experiments they did. we designed a molecule that was chiral with known absolute stereochemistry. So it wasn't both isomers in a racemic mixture. It was just one-handed stuff, not the mirror image stuff. And we changed the group on zirconium that was being added to the propylene monomer when it came in, from hydrogen to methyl to a polymer chain. And we figured out that if it was hydrogen and methyl, it was not very stereoselective. It didn't care which face of propylene, more or less. I mean, it's a factor of 2 to 1. But when you had a polymer chain growing, there was a group on the last inserted propylene that was going either up or down as propylene came in. And the interactions of that methyl group on the incoming propylene with that polymer chain substituent made all the difference. Suddenly it became, 100 times preferred one way versus the other, or even higher numbers than that. It got so perfect. It totally astounded these physical organic chemists when we did this, because usually you have to have some big difference between the size of the substituents. And a methyl and a hydrogen are not that different compared to what was thought to be needed. Or you had to have some sort of electrostatic interaction of of a group on the incoming molecule that was attracted by electronegativity difference or something with some substituent in it. So it wasn't just sterics, size. It was truly, there was also an electronic interaction that was either attractive or repulsive that was needed to get numbers that good. So there's this measurement that they use in determining the stereopurity of polypropylene, and it's called a pentad, but you don't need to know that. You just need to know that it can be as high as 99.9 or greater percent using one face of the propylene rather than the other. So the stereochemistry there is make or break. And the properties, the desirable properties, don't go up linearly with the stereopurity. It gets better and better as the stereopurity, better than linearly as the stereopurity goes up. So there's a case where I had to learn stereochemistry. I wasn't born as a physical organic chemist. I hadn't even learned that when I finished college. I had to learn it when I was a professor of chemistry. And I have some great colleagues at Caltech that would point me in directions to learn it, and I did.
Well, John, that's a great place to end for today. And next session, we'll take it all the way back to the beginning.